welcome everyone to Science Society, and of course, a special welcome to you, Romain and Emmanuel. And before we start, we usually do kind of an interactive type of introduction, if that's okay with you. I'll just briefly, mention that what we are talking about today, and then if that's okay with you, I'll ask you a few questions, so to have this kind of introduction, getting to know you in an interactive way. So today, Romain and Emmanuel will be talking about mostly about their work that was recently published on the double-slit time diffraction at optical frequencies, which is a really interesting experiment and study that came out. So maybe I'll start with you, Romain, since you're the first author.
Sure.
Kind of, how did you discover that you want to become a scientist? And what was basically, if you want to share a little bit with us, what the path was like, what elicited your passion for science, and then how did you become the scientist that you are today, or and being a PhD student where you are today? Thank you.
Sure. So I mean, I don't know how it goes for everyone has their own trajectory, but for me, I didn't know I wanted to be a scientist in a day. I think like most people, I was good in math in school. That's usually where it starts. And as you progress and you start to take more specific courses in high school, and then I applied to uni and I thought, okay, what are the best options for me? What am I good at? Where am I more likely to succeed? And also, what do I enjoy? And that led me to start studying mathematics and physics. And then as you progress through your studies, you start to learn what you enjoy and what you don't enjoy. And for me, first I realized I really enjoyed physics, and then experimental physics, and so that's kind of how I slowly um, slowly progressed into doing a PhD here in London. So I don't think it was a one day revelation, but more of a slow process of thinking, okay, yeah, I'm comfortable and happy doing this, um, and it's working for me. So that's kind of that's what got me into physics. I don't know if that was a good answer, but
Yeah, every answer is perfect, that your answer is like your path. So it's really wonderful to learn how, different scientists, discover what they want to do, and then get to be where they are today. And I think it's a really interesting, it's always interesting to learn about it. And today you were a PhD student, and you did your master's in physics from the University of Cambridge, and then your bachelor in physics, the Imperial College London. And you say that you're both, you're experimentalist, and then you say that you have also a strong theoretical background. That's not too common, is it, though? So that's really interesting.
no,
Did
yeah,
you,
it's true.
was it out of, necessity, or was it, that you kind of were very passionate about both and you want to follow both?
Um, well, it's I started doing mathematics in undergrad, um, and then I transferred to physics. And when I first transferred to physics, I was doing a lot of theoretical courses, and I was enjoying them a lot. But as I was progressing, uh, I realized that through internships mostly, because I think it's quite funny, but most people who do labs and experimental work in undergrad in physics kind of hate it because it's often fairly tedious and boring experiments. But I did a few research internships, and really got to see what was happening in a real research lab, especially in so nanophotonics, which is these labs where you study the interaction between light and matter at very small scales. Um, and so I kind of discovered that pleasure of like kind of you know uh, like putting your hands in there and experimenting. So it's kind of a DIY approach to physics. And so that's how I slowly moved towards experimental physics. So I started taking experimental projects, um, and then um, and then doing a PhD, like a mostly experimental PhD. So I really went from doing a lot of theory and very little experiment to the opposite, which shows that you're never really set on a precise path, either during your studies or your career in general.
Yeah, I think that's really important to stay flexible like that. Yeah, that's really interesting. That I wonder if either more people that say kind of yes to coming here to share their research here are just more open to different things, where if people that have this really interesting research, in high impact journals and so on, that are in general more open to different challenges and collaborating with different fields. So we are still I don't know if it's just a very biased way of, because I feel like a lot of speakers that come here are kind of that way. So it's just a really interesting thing to learn about our speakers here. Thank you. And Emmanuel, you're a Simons Fellow at the ALO Group Photonics Initiative, and you're at CUNY, New York. And but you were also at the Imperial College London as a student, as a master's student, and then later on you had won the doctoral prize. You were a doctoral prize fellow at the Imperial College London, and then later on did your PhD at Londra Regno Unito. So if you want to tell us a little bit about your path to become the researcher you are today, was it like a childhood dream, or what brought us to this point to talk with you here today? Thank you.
Thanks for the question. Yeah, for me, it kind of emerged as the thing that I liked at the end of my studies. For before the end of high school, I was very much into music. In fact, it turns out, and eventually, I was from a small place, and I come from a small town in Sardinia, Italy. Um, but yeah, eventually, those dreams kind of, you put them in a drawer, and then I had to. My default option would have been becoming a dentist, like most of my family. But in the end, that felt like the rest of my life would have been kind of already scripted, and that I was dreading that very much. Like as an 18-year-old, I was dreading a lot of things. But then I kind of looked at what I enjoyed the most, and what I enjoyed the most in school was really physics, and in particular electromagnetism. And as it turns out, it's not like I was so passionate about math itself. I appreciated it as a tool. As it turns out, I liked building things when I was in high school, like little like demonstration experiments and all of that. And so for me, it was a little bit the other way around. Then when I went to uni, I found that what I really enjoyed was theory, but I still maintain it, throughout my career so far. I always try to keep a toe on, not necessarily on the experiment itself, but on like physical insights. I think one risk of theoretical physics is to kind of lose contact with physical insights. If we think of if I think of the physicists that I really respect the most, they are the ones that actually manage to convey and to kind of stay in touch with the physics behind the math. So I try to keep that, and now as a theorist, it's not easy to collaborate with experimenters sometimes, and it's probably the other way around as well. I would imagine, Roman. But it's a very fulfilling endeavor, because it kind of forces you to, for one thing, um, try to see things through a different, from a different eye, from a different view, from a different point of view as well. There's always, coming from the theory side, there's always all these things that would be great to do, and then there's a much smaller set of those that what is realistically doable. And so in the case of this project, particularly, that, with through lots of coffee cups and discussions with Romain, and with the group of Riccardo Sapienza and Stefano Vezzoli, we came up with a couple of projects that where we could really find interest, both from the theory side and from the experimental side. So that's kind of when the two manage to meet. That's always very exciting science that emerges. So.
Yeah, thank you for sharing that. That's yeah, I totally agree, and that's wonderful that well, first of all, it's only the second time of all the speakers that I heard that somebody is rebelling by studying physics. We had one speaker before. She said a very similar thing. I think her parents wanted her to become a doctor too. And she
I still
studied
became a
physics.
doctor, just a different one.
That's really interesting, and a lot of speakers, interestingly, also have like a parallel passion for music, or still practice or play a lot of music, which is also really interesting. And yeah, I think in general we should have more time to freely discuss our ideas, and then ideally get funding for ideas like that we come to like emerge out of these situations that are kind of just conversations at dinners or something like that. So yeah, it's wonderful that this became reality then. And so thank you for sharing this kind of peek behind the curtains. And yeah, the slides, as I said, are pinned on top for everyone to see. So if you want to now go into the slides and present, the research, the stage is yours. Thank you.
Okay. So essentially, this experiment on double-slit diffraction in time is kind of part of a research, like a broader research theme, which is controlling frequency, or in other words, color, in time-varying media. And this is a collaboration between essentially the experimental and theory groups of Riccardo Sapienza, who's the lead principal investigator, and so Emanuele, who kind of came up with the original idea along with Stefano and John Pendry. And yeah, it's a very interesting topic, which essentially stems from trying to control light waves and their color. So if you look at slide 2, when you go to the fundamental question, what is light? Well, a lot of people say light is a particle, it's a photon, and because of that, you can say it's a ray. So it has like a very precise trajectory, just like if you throw a ball, you see the ball moving to a precise point in space and time, right? And so you have really cool art here by Berenice Abbott, which I believe is exhibited in the MIT Museum in Cambridge, Massachusetts. Now, if you move to slide 3, you can see that you can also observe wave behavior from light, and that is because light is well known now to be both a particle and a wave. And essentially, what we're trying to look at is how waves behave and how we can control them. So if you move on to slide 3, one of the main main ways and like main how do you say variable to describe waves that we use in general is phase, and phase essentially describes how your wave oscillates. So you have a wave that's propagating. It's this kind of undulation that you see here in red, and so its amplitude, which is how high it is. So you can think about a wave in water, can be described by the phase of the wave. And this phase varies through space and time and takes different value depending on if you're a high or a low or somewhere in between. And this is what we're trying to control in general when we try to control light and when we trying to control waves in general, is really trying to control that phase here. And so you can create structures that control color by interacting with phase. And notably, we got really, really good at controlling phase in space. So if you move on to slide, I think it's slide 5, yeah, you can see this painting of a flower, which is actually not really a painting, but more like millions and millions of these very small structures. Well, actually 18,000, which is not that much. And essentially, each of these little pillars that you can see on the bottom right will change the phase of light, will interact with different colors in different ways, and will send us a specific color. And that's what allows us to control, for example, the color at each pixel in this painting. So here what you're seeing essentially is a lot of these very tiny pillars of glass being emitted by light, and what you see on the other side is the different colors coming out. So that's the first example. A second example is quite funny. If you move on to slide 6, is in researchers from ETH Zurich, what they did is they printed a very small structure onto chocolate. So you can do that, and they do it in a lot of in a lot of shops actually. And essentially, you can observe rainbows coming out of chocolate because they have these very small structures that control the phase of light and can separate the different colors in that way. So essentially, with modern technology, we're very good at controlling the phase of light with spatial structures. And our research really tries and moves on to creating structures in time, and thus to control the color from structures in time. And so if you move on to the next slide, you can see that essentially the frequency, so the frequency of a wave describes the color of that wave, is essentially corresponds to variation of the phase in a certain time, which is the only equation that you'll see today on the left. And essentially, yeah, if we change phase in time, we can change the color. So what do we do? How do we do it? We take a material in which a wave is propagating, and we change its properties. And by changing its properties, we see a change of the phase of the wave that's propagating inside. And in general, that's what we will be talking about is time-varying media. So it's these media whose properties change in time, and that will affect waves propagating inside. So if you look at slide 8, there's a lot of ways we can control that way. It doesn't just apply to light, but it applies to all scales. So you can look at water waves, for example. So just on various scales, you have water waves, sound waves. So what people, for example, are very interested in is materials for shock waves from explosions. So you can imagine some devices that can protect you from an explosion or any kind of blast. People working in radio waves and communications. So that's actually, I know, a big theme of research in Emanuele's group in New York, which is RF waves. Then you can do faster and faster processes. So you can look at waves with electrons, but also what we call magnons, which are like kind of waves of magnets like attracting and repulsing each other and propagating in that way. So you've got all sorts of waves. And then you arrive to extremely fast waves, which is essentially visible light. And the faster these waves oscillate, and the more difficult it is to control the phase. And the reason for that is because you kind of got this principle, which means if you want to control something that oscillates at a speed, you need to change your media at the same speed. And our problem is, if you look at a water wave, well, you can see the wave moving by eye, but light wave you would never see oscillate by eye. So you need to be able to kind of like change a medium, so do a time varying media on these very, very fast scales. And so you can think about like trying to flick a switch very, very fast. So it's very tricky. And what we use for this, what do we use to control light? Well, we use more light. Essentially, if you move on to slide 9, you can see that we use a laser pulse to change matter. So essentially, what's a laser pulse? If you look on the left, you have this kind of graph where you see this kind of curve going up and down, which is called the Gaussian curve. And so the x-axis is the temporal coordinate, while the y-axis is the intensity of the wave. So essentially what it means is that you have your intensity going up and down within a certain amount of time. And we can make these pulses very, very, very short. And essentially we can bring them down to hundreds of femtoseconds. So a femtosecond is a millionth of a billionth of a second. So that's very short. And these laser pulses, that we're going to use them to shine them on a medium. And what's going to happen is when you shine light on the medium, the medium is going to react to that light and kind of change properties. And it's going to change properties within the time scale of that pulse. So that means that you can change a material, as you see on the right, within tens of femtoseconds with very strong amplitude just by using these laser pulses. And the material that we use is indium tin oxide. So that's a very popular material in solar cells or in screens. It's very interesting because indium tin oxide is conducting, but it's transparent. So that's why we use it in our screens, is so that you can bring the electricity across your phone screen while you can still see the light coming out of it. So moving on to slide 10, you can see, for example, you have this weird graph on the right, and essentially you kind of see that line, which tells you about which color the light that's propagating in the medium has. And essentially, if you make the light that's propagating in the medium arrive at the same time that laser pulse that I talk about, which we call the pump, arrives in the medium. So you have a pump that arrives with a lot of light, changes the material properties, and then what you have the probe, which is the light that we want to modulate, that arrives at the same time. Well, you see that jump here in the graph on the right. So if it arrives precisely at the same time, suddenly the color of the probe will change. That's kind of like the basic building block we're trying to have in our experiment, is to do these strong changes in color by inducing these very fast changes in the material. So to talk a bit more about our experiment, well, I think I should start by introducing Young's double-slit experiment, the classic experiment, which was done 200 years ago. So we're talking about very fundamental physics here. And it's a very interesting experiment. It's a very important one because it's the experiment that, amongst other things, proved the wave nature of light. So before Young, people weren't exactly sure about the nature of light, and a lot of people, including Newton himself, thought that light was a particle only. And Young was kind of inspired by another phenomenon that was well known at the time, which was the beating of sound waves, to do that same experiment with light. So in Young's double-slit experiment, if you look on the left, you have light coming out of two slits separate in space. And then as they propagate through these slits, they're kind of diffracted, so you can see them expanding. You see the propagation of the light expanding across a whole range of angles. And then you see it creates this kind of lines, these bright lights and these dark lines, which we call interference, and which corresponds to the two waves coming out of each slit. So you have a slit on top and a slit at the bottom with waves. Each one has a wave coming out, and what these two waves do is they interfere with each other, and they can add up or they can cancel each other. And that's why you see this kind of pattern where you see bright lines and dark lines and bright line and dark line going away from the center and like decreasing in intensity. So we want to show that we can do the same things but in time. So by changing colors. So if you look at slide 12, so you can see if we control the phase in space, so that's what the two slits are doing effectively, is controlling how the phase evolves in space. Well, you see that interference pattern coming up on a screen in the distance. Now, if you modulate the phase in time, what we hope to observe is the same interference pattern. But this time, it's not like a spatial distribution that we'll observe, but more of a spectral distribution. So what this means is we'll see all our different colors oscillating in a way in a single spot. So you can think of a bright orange peak, and then superpose on it a red peak, and then a green dot and a blue dot. But the blue dot, because it's further away from the original orange, would be much weaker than for example, the green dot. So that's kind of what we're trying to do, is to do exactly the same thing, but seeing these oscillations in the color of the light. So what do we do? If you look at slide 13, we're looking at our indium tin oxide, which is essentially an ultrafast mirror. So you can see a little picture on the left here of our sample. So you can see it's just mounted in our setup there, and it's a very thin film. So it's only 14 nanometer thick. So again, for scale, a nanometer is a billionth of a meter. So we're talking about a very, very small medium. And you can see in red is the light we want to modulate, that we shine on, and then we can choose to reflect it or not. So that's going to be our kind of a slit in time. So if the light is reflected, the slit is open. And if the light is not reflected, the slit is closed. And then this slit, we open it and close it with another laser. So that's what you see on the right. You see these kind of two openings in time by shining a laser. And then if you look at the top, you can see the reflected light that we get. Essentially, we can control when these two transmitted light like when these two reflections in time happen with our setup. Okay, and then in slide 14, you can see, so we use a measurement apparatus which is called a spectrometer. And essentially, a spectrometer allows you to look and measure how much intensity you get at which color from light. So it separates all the colors and tells you, well, this color is stronger than the others. And that's what you're seeing here in the graphs at the bottom. You see in slide 14, at the bottom, the x-axis is the frequency, which is the color of light. And then on the left is the counts per second we get on our detector, which is essentially a camera. And so you see these little oscillations that I'm showing here, which is essentially the side of our oscillation pattern. So you can see these oscillations decreasing just as expected from what we talked about earlier. So if you compare slide 12 and slide 14, you can see the same kind of pattern appearing. And now if you change the separation between your two slits, so that is when they arrive, so as in, for example, on the left, the two times you reflect your light are separated by 800 femtoseconds a second. Now, if we make these slits closer in time, so they're only 500 femtoseconds apart in time, well, you see the period of these oscillations is going to change. And it's going to get, in this case, longer. And that's a very like typical signature of double slit diffraction. So it's really proof that our experiment is a diffraction in time, and that's a very that's a very powerful result, because It's never been done before with visible light. I mean, here it's near infrared, but that's very close to visible light. It's the same scale of speeds, and this formalism that we have, which is diffraction, is like very for physicists, it's very practical and very simple to approach. So it really gives us a very powerful tool with this very fast mirror that modulates light to kind of start getting control over the spectrum, over the color of the light that we want out of our sample. And now, if you look at slide 15, we had a little surprise, which was really nice when we did the experiment. We saw a lot of oscillations. Now, if you count them here on this graph, you might think, well, it's actually not that many. But if you're an experimentalist in physics, well, you know how hard it can be to get data. And so we expected to just see a couple oscillations, maybe a bit more. But here you can generally see a lot. And essentially, what dictates whether you can see these oscillations or not is how fast your material reacts to your modulation. So how fast you can turn your mirror on and off, how fast you can create these slits in time. And the real surprise here that it's much faster than we thought. So it's it's kind of a very happy finding. And the theory matches very well the experiment in our case. So it really confirms that our the speed of our modulation is higher than previously accepted. So just to wrap up on slide 16, I think if there's main things to take away from this paper, I mean, it's very rich in physics, but you can say that we've created a time-varying mirror with indium tin oxide, which is essentially what we call a temporal interface. So we can really switch on and off these slits in time, and we demonstrate double-slit time diffraction for the first time with visible light, which is a great achievement and very exciting for the future, because we might want to do more complex temporal modulations and other applications. And another great result is how fast this switching on of the laser of the material was, and how it really unlocks a new regime of modulation that we want. So yeah, I hope you've enjoyed this little introduction to the paper. Hope it wasn't too sciencey and too obscure. You've got a QR code that's a link to the paper on Nature Physics, and you can also check out Ricardo's group website, which is sapienslab.com. Thank you.
Yeah, thank you so much for sharing this and for this really beautiful presentation that visualized this really well. I wanted to ask you, Manuel, did you want to add something before we go into questions or comment on something?
Thanks, Katarina, and thanks Romain for the kind of overview of the whole paper. From my end, it's maybe we can also leave it for questions. Maybe I'm happy to discuss questions as they come up. It was what from the theory side, this work was a lot more challenging than I was expecting, in fact, and that really came out of the surprises that we realized were in stock for us in terms of how fast these materials respond to optical pumping. So how fast we can actually modulate matter and change the way it interacts with light that we use to probe it. And one of the main findings of the work really is that all the assumptions that the community had been making in modeling these theoretically these materials, really we needed to rethink them. And in fact, right now there's a lot of also theoretical effort in really coming to terms with the fact that these materials respond unexpectedly fast. That's what really from a theory point of view. Of course, the fact that these materials respond so fast. But then that opens the question, why do they do so? So that launches a new challenge for kind of theoretical state physics and light matter interactions.
Yeah, that would have been one of the questions why you think, how the explanation, what is the leading theory of the explanation um, why that is, basically.
Yes, yeah. This is of course a kind of developing, as I was mentioning, it's a fast developing kind of subject of discussion from the theory end. But what's emerging really is that there are what seems to be the case when it comes to modulating materials effectively is how many electrons are you actually dealing with. When we think of the density of electrons in a metal like gold, it's extremely high, and that means that in order to appreciably change the optical response of gold, which is dominated by electrons at optical frequencies, um, you really need to do a lot of work, and the amount of energy that you need ultimately ends up melting the gold. So that's kind of a no-go, or no gold, if I to make a pun. But these materials, the one way that some groups call them are low electron density Drude materials. But the point here is that because they have such a low electron density, and which is ultimately why they're transparent, as Romain was saying, it also means that we can modulate them very efficiently, and so that's why they allow us to modulate them and to achieve all these actual modulation effects, all these ultra fast phase changes of light, and therefore creating additional colors effectively out of light. There are still many mysteries in terms of how light couples to the vibrations in the material, and that's all like kind of in the making. They are really developing a deeper understanding for what goes on. And this idea, of course, underpins other materials as well. By the way, that have made the headlines recently. Graphene is one of them. One of the great promises for graphene and 2D materials is that because they have a much lower density of electrons, if we pump them, if we shine light on them, we can actually modulate in time their electromagnetic response very, very efficiently.
Yeah, thank you so much for that answer. Um, I would, I'll ask one more question, and then I know Oppenheimer and Zoltan and Aditya had for sure also questions. Um, so what I know it's a kind of very broad question. I'll start with like very broad question. So what do you think would be longer term the applications from the results that you see? Would this, could we apply this to signal processing or maybe even neuromorphic computation? Or is that still, too far out to think about that?
I will leave this one to Romain first, at least, because I know that your group is interested in optical computing, so maybe you have a better shot.
True. Well, it's a tricky question because there's a lot of things you can start from where we are at the moment. So indeed, Emmanuel mentioned computing, and a lot of people are thinking about doing some machine learning using these materials because essentially machine learning right now is mostly done on GPUs, so graphical units, and a lot of people are thinking about turning towards more analog machine learning, which would require a lot less energy and power. Because right now machine learning is essentially polluting a lot. It's very bad for the environment, and it's also very expensive computationally. And what you need to do analog machine learning is highly nonlinear system. And this our medium that's changing very fast in time is a perfect example of these very nonlinear system. Um, so you can do so a lot of people are considering doing neuromorphic, what we call neuromorphic computing. So it's a form of machine learning that kind of reproduces the way neuron works in a brain, which you might be more familiar with. But there's a lot of things you can do, and as you said, you can think about signal processing, because um, now that you're starting to get control over color. Well, we mentioned structuring in time and structuring in space, and now you can think, well, what if I do both? um, and you start to you could think about creating very complex structures that can what we could call like an ideal light multiplex. So that could really take any form of inputs and give you any output that you want with light. So that would be very useful for communications and other applications that um, we can only imagine. But maybe lidars and a lot of people use these kind of systems to do um, how do you say augmented reality or shape recognition, um, all sorts of applications that are more or less ambitious, but that hopefully we'll get to see one day.
Yeah, thank you. And I had one more question that I wanted to ask before you you mentioned that the propulse um, broadened, like the spectrally broadened with the frequency bandwidth that were away from the carrier frequency. What do you think? Does this contribute like to our understanding of spectral modulation and so forth? Like, if you could explain that maybe a little bit more. Thank you.
Sure. So here, this is really touching to the topic of diffraction. So to give you an example, if you look at waves entering a harbor in in a little like in the coast, um, you can see this kind of wave which was arriving, with really a flat wavefront, and then it enters the harbor through like a fairly narrow entrance, and you see it propagating spherically, right? Um, and this is an example of diffraction. And what this means is, for these waves entering the port, it means it broadens the range of angles at which the wave propagates. And when you do this in time, it broadens the amount of colors that are in your spectrum. So at the beginning, you can think of only one color, and then you go through this kind of slit, this kind of narrowing for the wave, and then you see more colors coming out, a wider range of colors. And this is actually an effect from the single slit. So if you have only one slit, you see this broadening. So you see more colors appearing. And this in itself is a proof of is diffraction, but we wanted something stronger that could reveal more things about our system and that was more convincing, and that's where the double-slit experiment comes in, because in the double-slit experiment you have the effects of both a single slit and the presence of two slits. So what happens is you see the broadening from the single slit effect. So you see all these frequencies appearing, but from the what creates the oscillations is the double slits. So you can think of these kind of very large of extent of newly generated frequencies, and then you see the up and downs that come from the fact that you have two instead of one. And that's why if you look at slide 14, you see if you change the distance between your two slits in time, so the different arrival times, you see different ups and downs than before, but the effect of the single slit is still the same. So you still see the same extent of generated light, of generated colors. So
yes, it's really this broadening and the oscillations are all diffraction effects here.
And then it was also mentioned that basically the shape of the time slit is important. So how did you come then in the end with the shape you settled on, and what does it, what does it mean that you need, like, do you need a very specific shape? Are there many types of shapes that would come to the same result, and what do you think it tells us?
Maybe I'll leave this question to Emanuele. It's a bit more theory.
Yeah. So how sharp, how sharp the slit is determines uh, how many oscillations you're going to see. Imagine if it was very slow, if it was very kind of blurred, if you like, you wouldn't really produce those oscillations in a limit where the rate at which this change in time occurs is very slow. We would say adiabatic. It changes very slowly compared to the oscillations in time of the wave. You would not see these fringes. So the visibility of these fringes only starts becoming appreciable once the speed at which the material is changing starts becoming comparable with um, uh, the period of the wave, with the rate at which the waves are oscillating in time. So, and as you say, like, what is there a preferential way? Is there an optimal way? Well, each profile will give you a different response, but in general, but in the limit where these slits become infinitely sharp, like you would have, a perfect hole, for example, they all converge to the optimal, if you like. The best that you can do is basically a situation where the slit goes literally closed, open, closed, like completely 100%, within basically effective within an interval of time which is much faster than the temporal oscillations of the light waves.
Yeah, interesting. And do you think that your results kind of, that models have to be, I think you mentioned it a little bit, but just to make clear for the audience, do
Mm-hmm.
models need to be adjusted because you had kind of a discrepancy of much faster temporal dynamics? Do models have to be adjusted like theoretical models, or yeah, you mentioned that there's an ongoing study about
Mm-hmm.
materials and so on, but um, that's more on the experimental side, but is on the theoretical side something that needs to be adjusting?
Yeah, so the theory really kind of has the ball right now in terms of um, uh, understanding uh, why this is what we see is where we see so many of these oscillations, because the way that we initially model the system, there's a figure in the supplementary material of the paper where we use an established a method that had been used for other works. However, a method generally will hinge on some parameters. We that method had certain assumptions, like the change in the optical response, in the quantities that describe the optical response of the material changed linearly with the intensity of the pump pulse. And unfortunately, what we found is that that assumption was very not very much. It didn't hold. Any way that we tried to model what we were observing based on that assumption failed. And when that fails, of course there's some disappointment about it from the theory point of view, but there's also some excitement in that there are more questions opened. And in fact, ultimately, what ended up doing the job was really this diffraction model, where we can basically ask the experiment, this model, does this model describe the experiment? And if so, what is the rate at which this modulation has to happen in order for this model to describe the system, to describe what we observe. And tuning up one parameter, the model precisely reproduces the entire spectrum of harmonics that we observe. So from a theory point of view, at that point it was hooray, because um, there's a lot of physics there that this model can reproduce, with essentially one assumption, which is the speed at which this change in the indium tin oxide is happening. So that's at the moment the best theory that we have, and it's a theory which is somewhat simpler than other theories that have been put forward before, which still rely on their own assumptions, by the way. But it turns out that those assumptions don't really hold, and so this theory kind of takes a step back, takes a bird's eye view on the physics at play, but it also allows us to make very powerful predictions to about how fast this modulation is happening.
Yeah, thank you for those answers. And Zoltan, did you have a question? Zoltan was a previous speaker here. He talked about different types of perceptions of time in children and adults and how it switches during development. So he was really looking forward to this talk. So Zoltan, welcome back. And did you have a question or comment you wanted to add? Maybe he's away from the phone. I know it's very late where he is, so. And Hansen, I see your hand raised. I tried to invite you. If it doesn't work, check in your profile. Yep, there you are, Hansen. Welcome. How are you? Please ask your question.
Good. How are you, Katerina? I came in really late, trying to understand like quickly your work. So if I characterize it wrongly, please excuse me. The is it basically, is it good characterization, or maybe oversimplified characterization? You shoot two pulses of light in succession, basically because you can have linear superposition of light, and then with the time, with a, let's say, bump or whatever time, time domain shape you want to have it, maybe maybe a thin Gaussian or some other shape, and then you look at the diffraction pattern of the film or crystal, but then isn't it you can just do a Fourier transform, and then superimpose the two pulses. For the thin pulses, basically the Fourier spectrum would be uniform, and the thinner it is, the more flatter the magnitude in the frequency domain would be, and then but there's a phase shift. In the frequency domain, because you have time shift, and then just for it transform this phase shift and then superimpose them together. But of course, it depends on the material, the crystal, whether it's crystal or not, I'm not sure. You have Bragg diffraction, and so depending on the response time of the crystal, you add in that factor, and then you get the profile in the frequency domain. Would that be a kind of maybe simplified characterization of the experiment?
Thanks for the question. Yeah, I can try to answer this question. So we have two models in the paper that we use. One of them is much more kind of quantitative, and it's based on methods that people have used on other experiments as well. And it turns out that the main features are there. What we could not reproduce, qualitatively, that model reproduces the features that we see in the experiment. But quantitatively, there's no way that the assumptions about the scaling of the change in the dielectric properties of the material, that in the optical response to the material of indium tin oxide, there's no way that those assumptions could allow us to quantitatively actually model, reproduce the results that we were seeing in the experiment. So we took a step back, and yes, the model, a simple diffraction model, is much simpler than what we were using before, it turns out. However, here is a much simpler model that actually not only qualitatively reproduces the data, but it quantitatively it reproduces it quantitatively as well. So the phenomenology is there, and we know that a more kind of, if you like, sophisticated method, which still has certain quantitative assumptions to it, does reproduce the physics that we see. Now, what the sum of the two models suggests is that we need to upgrade the models that we're using at the moment, the more sophisticated models that we're using at the moment, in order to be able to reproduce these results quantitatively with something which is more ab initio. If you come from, I'm sure you.
Yeah, of course, first principle.
Yeah,
Yes.
yeah, of course, yeah. Yeah, ideally, we would like to have something that's more from first principle, but we stopped there at that point because we didn't want to make just wild assumptions about the underlying optical response to the pumping. We wanted to, and there was no like at the point where the results were, at the point where we were with the project. We between the two methods we could have something that was solid, and we thought there was no maybe that it's good also for the community to get this result out there and have other people that are experts on non-equilibrium dynamics, which is really what is happening there. And now there are follow-up papers that are demonstrating that that there is a lot of rich non-equilibrium dynamics that goes into explaining these phenomena. But that would have kind of taken away that would have kind of drifted away from the theme of the paper, of the kind of project, of the whole idea. So we try to not go down that rabbit hole for within this paper. With that said, yeah, I agree with you. It's one of the two models is kind of more kind of simpler, but between the two, I think we have a solid idea of what's going on.
I see. So I suppose that when you say the going down the rabbit hole, controlling down to depth, that would be interaction of the light photon with the
Yeah.
atomic structure, the excitation, the quantum excitation, and then release the optical pumping and all that. So, but I understand that you're doing it maybe from a more phenomenological perspective, right?
Exactly. Yeah.
Um,
Exactly.
so, but the thing is, but why from the diffraction, isn't it? Isn't it just simple linear superposition? I mean, why would why? What is this? What is special about putting two pulses together? I mean, isn't that
So
you can
I
just
think if I can just step in, sorry. So it's not two pulses. What we are observing is a single pulse.
but you can
So
shape it
it's not
different.
just,
No, okay, go ahead. Sorry.
yeah. So we take a pulse and we shape it differently to have something that would look like two pulses. Um, I think what's interesting there is if you think is that technically you could do the same experiment with a single photon. So you raise a very valid question, which is, what does it mean? But you know, if you did the same experiment with a single photon, so just one particle, then you would have something very similar to the experiment of which slit did the photon go through, right? And in that quantum experiment, you see the interference pattern coming again if you do that experiment with a single photon a lot of times. But if you start looking at which slit the photon went through, then the interference pattern disappears.
Sure.
And essentially, our experiment, amongst other things, shows that you can do the same thing in time. So if you did the same experiment with a photon, it could come out with a probability following that kind of like oscillation with its frequency. So I think in these regards, in this aspect, it's kind of different than just mixing two light pulses together. And
But
so yes, yeah. Sorry, go ahead.
no, got you. But is your treatment classical or quantum?
So the treatment is classical. But very luckily for us, like a classical Gaussian pulse behaves exactly in the same way than the probability function of a single photon. So so that's why you can kind of predict your properties from the classical experiment.
Yeah, but the thing is, I mean, it is if it is classical, it's optical read domain. Um, the I mean, but well, okay. So mathematics is the same, right? So the two pulses and one pulse and shaped into we have two bumps in the time domain. It's the same, right? I mean, the just linear superposition, and I mean, if it is one photon, then experimental, it has a very stringent experimental restriction or requirement. But if it is classical, then the I don't know. I don't know why the what's the necessity for two pulse. I mean, you can just derive the result from one pulse if you looking at the material response. I don't know. I must miss something.
No, I think you're right. As in, it's a lot easier to do the experiment with a lot of photons in a classical regime rather than a quantum regime. And at the moment, I wouldn't dream of doing that experiment with a single photon. Now, in terms of the mathematical aspects, yes, you can always say that a single pulse or two pulses, it's all the same formalism. I think from a practical point of view, it's quite important to us that we can just take one pulse that we want and get any other shape that we want out by doing Fourier transform. I think it's really cool. Maybe Emmanuel, you have an opinion on this, maybe from a more theoretical perspective.
So from it, I mean, I think we were equally surprised when we realized that we could just model it in that way. And I said the theoretical idea for this project, there were a bunch of theoretical ideas that emerged during the course of this project, because originally we were trying to model the experiment. That was the key. But then we came across some work on this idea of time diffraction, and it turns out that it's less trivial than we thought. Like, not every wave equation will give you this effect that we observe. For example, in the case where one simply sends a wave normal to this shutter, if you like,
When you say normal, you mean 90-degree perpendicular to
so
the.
if you simply shine a plane wave against, normally orthogonally against a shutter, different wave equations, for example, the Schrodinger equation and Maxwell's equations, will give you very different answers in terms of whether you see or not this effect of transients, basically. What you see there is a transient. And we were not even sure whether we would see this. This would be an effect that was allowed for our scenario. And bear in mind, this doesn't contradict. This is all paper by a guy called Moshinsky in 1950s, 52 or 58, where he goes through different wave equations, and what he finds is that some of them, if the time derivative has the same order as the space derivative, you will see this effect, and you will not see the effect. If you have the Schrodinger equation where you have first order derivatives in time and second order derivatives in space, then you will see the effect. But then if you start working with the resonance, like in our case, you can see the effect. So there's a kind of broader umbrella on top of these results. I agree with you that the way that ultimately a diffraction model that you would do in the spatial domain maps exactly to the time domain, that came as a surprise for us too. We were certainly not expecting to reproduce all of that just with a simple diffraction model. But then from a quantitative, the thing that the surprise there from the theory point of view is much more in the quantitative speed at which we can see these fringes. The amount of fringes that we can see, and therefore how fast this material is responding. I agree with you. There's no like very advanced theoretical physics in the work. A lot of it is basically one of the main findings is basically the models that we are used to don't work. We need to come up with better ones. And the other one is here is a very simple model that somehow reproduces all the data. And it turns out that this, because normally materials don't respond so fast, these fringes had not been observed before. Yeah, so that's the other. It took basically working with these transparent conducting oxide to be able to see all these fringes.
I see. I guess it's that's my kind of question. I suppose that's because the material property of the target, that's more interesting, right? So the how fast it responds, the atomic structure, the
Absolutely.
yeah, and then and then you mentioned Schrodinger's equation. I would say, I mean, I don't think that the wave, I mean the electromagnetic wave could be described by Schrodinger's equation because
No, absolutely
there's
not.
no mass, right?
Yeah,
Yeah, and you probably, if you want to use the quantum version of Maxwell equation, you should use the quantum field equation, right?
yeah,
The
yeah.
so yeah, I don't know if you consider, I mean, but that's more in the realm of the photon material interaction than just the diffraction pattern, right? That's the
Yeah, absolutely.
probably more interesting.
Yeah, absolutely. This is the center is of all of this is like matter interactions and how fast we can actually modulate light, rather than the whole like mathematical infrastructure there. Um, that was not one of the key points of view of the paper. In fact, I think that the review reports were published with the paper, and one of them in fact praised the fact that the model was really simple and in fact but still described the data so accurately. Um, yeah, so I agree with you. The key novelty here is not in the techniques that we use to model the experiment. In fact, that was kind of, as I said before, it was taking a step back from a theoretical point of view. We didn't push farther into whatever was going on in terms of non-equilibrium dynamics, but rather we took a step back and look at what we were seeing in terms of um, scattering.
Gotcha. So I'm just curious. What's the original, the one that your method replaced, the more simpler method that replaced, which is, as you said, more complicated. What was that treatment?
Yeah, so in that treatment, you basically assume that the plasma frequency varies linearly. So basically, essentially the electron density varies linearly with the intensity of the pump. And it was clear that the timescales would not match. So the speed at which the material would have to respond in order for that assumption, the material could not be responding linearly to the intensity of the incoming pump, and that if you check the paper and also the other paper, the previous paper where we used that model, there are the main difficulty is, I think, really in that assumption that the response is linear with the intensity, and in fact from another group now it turns out that not only it's not linear, but you cannot even describe it as a polynomial. Basically, the response they say is very non-polynomial, which I still need to really discuss more with them. But the point is that the conventional way that one describes nonlinear optics is that you expand the optical response in terms of increasing nonlinear contributions, and typically you take the first one or the first couple of terms. And so far, the community had been simply saying that the plasma frequency varies linearly with the intensity. That really turns out not to work for this system. And the really correct way of going about this is to write down an equation for the distribution of electrons, and then consider electron photon interactions, electron phonon interactions, electron-electron interactions, and quantify all of those. And so it's a much more it's a much deeper computational exercise.
Yeah, I would think so. So the original, I suppose. I mean, I haven't looked at the paper. My guess is that you said linear response. Is it basically treating it as a kind of a one bulk, and without looking at the kind of the I don't know if it's a crystal or anything, the crystal structure and then scattering. Would that be correct as a one bulk? Okay.
Yeah. The properties of the bulk material are where we assume that we have a modulation.
Gotcha. All right, great. Thank you very much.
Thank you for your interest.
Yeah, thank you so much. And I wanted to just, I know we've been going on over an hour and almost 15 minutes, but I just wanted to point out that this really fast switching, I think it's really interesting, especially for hopefully future applications for neuroimaging, to record, in real time brain imaging processing that's going on a larger scale. But yeah, as we discussed before, like devices, like neuromorphic devices, this will be really exciting to use that fast switching. And we had the speakers here on Monday that are using these materials of nanowires to kind of have a nanomaterial for neuromorphic devices. So this would be a very different approach. But would you say that there are specific information processing that would be more suitable using this optical approach versus like nano wire approach? Do you know about these? And would you say that there are applications where this optical approach would be better, or yeah?
It's a good question. I think nanowires are like a very great device, a very interesting tool. But they usually belong more in the what we were talking about earlier, the spatial structuring. So you could definitely try and imagine a device that combines both spatial and temporal, and especially because I know that people have made nanowires with indium tin oxide, which is the material we've used. So there's definitely potential for this. But it's true that at the moment the bridge hasn't really been done yet.
One of the
Yeah,
go
no,
ahead.
please go ahead. No, I wanted to point out that this nonlinear characteristic is in both, and for both materials, basically, the important one to basically generate different types of memory, and that is more human-like. Um, so there, and from this aspect, it has that commonality, but I wonder if there's aspects, maybe, if you do visual processing versus let's say priming of information, maybe that would be, maybe, to point out to the system what memories would be more important, and they should retain longer or something. If that would be maybe something that would done better in this nanowire materials, and then the optical processing maybe more for information that needs to be really fast. And yeah, but I don't know, I'm not that's not my field, so thanks.
I mean, I don't know what you think about it, but I think it's a very valid point. But I think it's a question that still has to be answered. I'm not sure I can.
Yeah, so the people in our group do some optical computing, and I don't think they yet are thinking of neuromorphic computing. But maybe probably are thinking about it, but I don't think I haven't seen anything specifically on that yet. What people say about optical computing is ultimately it's going to be the good thing is it should be easily parallelizable. I don't think I would be able to make a sound argument in favor of either method towards specifically neuromorphic computing, because it's really kind of out of my expertise. So all I can say is that there is a lot of interest for optical computing at the moment. So far, largely based on fixed structures. But here we're talking about standard kind of analog computing, like running specific operations based on the structuring of basically of designing a photonic structure and building it. So basically doing calculations with light, and in an analog fashion. From there to what's better for neuromorphic computing, I wouldn't be able to tell.
Would there be a way of this metamaterials to kind of adapt to the information flow that comes in, or, as you said, for now it's a very fixed material, or does it, are there different types of materials that would be basically able to have kind of an ingrained information processing in the material itself?
Yeah, so I think the thing that the metamaterials world has in store in terms of optical computing is to have basically a dynamical tunability. That's really the next thing, meaning that based on, say, optical pumping or other ways of modulating, well, not really modulating, really just like retuning and adjusting the response of a photonic structure to whatever operation we want to use it for. There are multiple groups that are focusing on this problem. In the context of this particular paper, this is kind of one step further in the sense that, and therefore a step further from applications right now, because we're kind of probing the limit to how fast we can change now these materials. So it's not so evident yet whether this speed will be used in terms of the operation itself, like we said, in terms of frequency shifts and, like, varying, doing computations based on frequency modulation at near optical frequencies, or whether it's simply going to be like in a switching kind of picture where we can adjust the optical response of these optical structures in order to vary their response, their functionality on picosecond or sub-picosecond timescales.
Yeah, I think that the time resolution is the interesting part, because this nanowire systems don't necessarily have that. They are able to mimic basically neuroplasticity. So basically the system adapts like memories, like the neuroplasticity in the brain adapts to the memories. So that is possible there, but I don't think you have this fast and time resolution that the system could tell. Would that be something that the system could tell when which information came in at a higher resolution, basically, and give that way a more closer to, the opticals, or the optical system of the brain and retina and so on. I think combining those two would be really exciting, but I know that's probably a little bit in the future. So
Yeah, I mean, maybe Roman probably knows more about this, but from my end right now, it seems a little far-fetched, optimistic. But it's
Yeah,
good
I
to look
think
forward with optimism.
it's very much for the future. It's true that light allows us to observe and resolve very short timescales. That's the benefit of it. I think on the other hand, and people are working on it, but there's more problems when it comes to memory. So you were talking about storing information, and I think if people now can try and work towards reconfigurable devices, so changing the task that you learn to do, that is something that maybe you can see in a not too far future. And people in parallel are working on optical memory, but this is also not. Sorry, Emanuele. Do you like, maybe you know more about optical memory? I'm not really an expert in the topic, but I think maybe in a bit more further away future, maybe you could bridge the two. But I think to do things like what is done with these nanowires, there's there's still quite a bit of work to do.
Yeah, absolutely. I wouldn't be able to really push it. More into. Probably need to learn more about it to make a statement.
yeah, and if you have time for one more question, Lara is asking if this experiment has would have maybe also similar results in sound waves,
Mm-hmm.
yeah, or in other basically waves.
Yeah, so in this whole field of kind of time varying media really has had a lot of success, really, in the acoustics community and mechanical waves community, like water waves, for example. And the idea, of course, as Romain explained very clear at the beginning, is that these waves oscillate at much lower frequencies. And that's, of course, a double-edged sword, because on the one hand, yes, a lot of ideas, often more kind of even more fancy or sophisticated than what this experiment specifically showed, can be implemented. On the other hand, it's less. It's a lower target in the sense that it's less striking. That modulate what the this project showed is that materials can respond extremely fast, much faster than we thought before. So we're talking about several orders of magnitude, nearly 10 orders of magnitude faster than sound waves. So the acoustics community is very active in the context of time-varying media. In fact, if you Google time reversal imaging, most of the papers that you'll find will be about acoustics, ultrasound, and the reason is that we can digitally convert and manipulate sound temporally at speeds which are much, even with digital equipment, much faster than the frequency of the sound itself. So that there is a lot of course, potential for implementation, and also very fundamental studies on wave physics, which is kind of my main topic of research. But so there are certainly opportunities. They can be potentially less striking in the sense that it's less surprising how we know pretty well how fast we can play these tricks with sound, and because we can always use light, for example, which is much faster to modulate an acoustic system. In fact, I'm aware of experiments where they are using lasers to modulate very fast acoustic cavities with ultrasound in order to engineer pretty extreme time varying effects.
Yeah, thank you for that answer. And yeah, I am sorry that we went over the time, but this was such an interesting discussion, and it's such an interesting field. So thank you so much for coming and sharing your knowledge and your time with us. um,
Thank you so much.
and yeah,
Yeah,
I
thank you.
hope you enjoyed it, and yeah, good luck. I know you don't need it, but anyways, for your future research, and we are really curious to follow your, next publication and what comes out of your lab. So yeah, thank you so much.
Thank you, and
Thank you very
thank you,
much.
everyone. Take care.
Real pleasure.
Wonderful, and thanks everyone for coming, asking questions, sending questions. Yeah, and if you like discussions like this, follow us. We'll have on June 5th at 7 p.m. EST Dr. Fukasawa coming to present from Japan, and he will talk a lot about his latest paper, Electrical Potentials in the fungi system, that he could record after a rainfall event. It's really interesting how these fungi systems communicate with each other through electrical signals. There's a lot of research coming out of fungi and out of plants. So I think this will be really interesting. And yeah, so thank you, everyone. Thank you, Manuel. Thank you, Romain. It was a pleasure meeting you. And I'll close the room in 3, 2, 1. Bye, everyone. Thank you.
Thanks.